In this video, we're going to begin discussing inverse functions. So some functions have an inverse function and some do not. That's one thing that we're going to look at in this video is when does a function have an inverse function and when does it not. If our function we're talking about is denoted f of x, then the notation that we use for the inverse of f of x is this, and that's just read as f inverse of x. That -1 is not an exponent. It's not an exponent of any kind. No, there's nothing happening with an exponent. There's no reciprocal of anything. That's not at all what that is. It's just simply a notation. It's a notation to represent the function that is the inverse of the function f of x. So we've said what it's not. What is it? What would an inverse function look like? You might be wondering. And we can kind of look at this with a table to start off with. So if a point AB is a point for a function f, then the point BA is going to be a point for the inverse of f. So to find the inverse of f, we're just taking each point and switching the x and the y coordinate. So let's do that for this function here. So for example, for the first point, we're going to switch and it's going to be -8, -2. And when we switch the x and the y coordinate for the next point, we get the same point, but that's okay. And that's going to happen a couple more times. And then the last point is 2, 8, so the inverse will have the point 8, 2. Now, one question that's going to come up is the inverse a function, right? So that's why we said some functions have an inverse function, because you can always find the inverse. You can always take the table and switch all the coordinates of all the points. But the question becomes, is the resulting relation a function or not? And remember, to be a function, each x value can only give us one y value. So if we look here, we don't see the same x value showing up more than once. So this is a function. So I'm going to go ahead and finish that function notation there. We say these two functions are inverses of each other because if I started with the first table and I switched all the coordinates, I'd get the second table. So they're inverses of each other. It doesn't matter which one is labeled f and which one is labeled f inverse. In this case, I used a specific function to generate this table. I didn't just make it up randomly. You might recognize this. This is sum of the values for the function x cubed. So 2 cubed is 8, 1 cubed is 1, etc. So then what do you think the equation of the inverse would look like? Well, we have the point 2, 8 because 2 cubed is 8. Over here we have the point 8, 2 because the cube root of 8 is 2. So the functions x cubed and cube root of x are inverses of each other. Now let's see what happens when we compose the two functions. We've talked about function composition in a previous video. That's where we're just substituting one of the functions inside of the other. There's two different notations we can use for that. They both mean the same thing. Both of these mean we're taking f inverse and substituting it into the function f. So here that means we're taking cube root of x, substituting it for x in the other function. So we're going to have cube root of x cubed. And what we get from that is just x, right? If we cube a cube root, those undo each other. We just left with x. Well, let's see what happens if we compose them in the opposite order, because we've seen that function composition does not always give us the same result if we change the order of the functions. So if we do f inverse of f of x, that means we're taking the function f and substituting it into f inverse. So we're taking x cubed, substituting it into the other function, and so now we have cube root of x cubed, but they still undo each other and we get x. This will always happen when you compose two functions that are inverses of each other. You'll get x, and that's one reason why we care so much about inverse functions, because if I have an equation and I have x cubed on one side and I want it to just be x, what do I do to both sides? I take the cube root. I do that because I know if I apply that inverse function, then I'm just going to get left with x, which is what I wanted. Same if you had cube root of x equals something. To solve it for x, you would cube each side. So that's one of the many uses of inverse functions, is when you're solving an equation, you can apply the inverse function to both sides to get the variable. Now, I mentioned earlier, not every function has an inverse that's a function, so we need to look at when does that happen. So if we have just the function x squared here, I've written some of the values for that function. Let's find the inverse. We can always find the inverse. We can always switch the coordinates of all the points, and then the question is just, did we end up with a function or not? So if we switch the coordinates of the first point, we got 4, -2. Second point becomes 1, -1. Third point is 0, 0. Next point is 1, 1. And then we'll have 4, 2. So, does that second table represent a function? Hopefully you said no. Here's one example of an x value giving us two different y values. We have also another pair of points we can see where that's this case, and if I had written out more points in the original table, we'd see even more. But as soon as you find one example of an x value giving you two different y values, you know that's not a function. So no, the function x squared does not have an inverse that is a function. Well, why is the inverse not a function? Well, we've identified those duplicate x values. Where did those come from? Those came from these points here, where we had duplicate y values. So the original table is a function, right? The original table doesn't have any duplicate x values. X squared is a function. But because it has duplicate y values, it's not a one-to-one function. X squared is not a one-to-one function. It would fail the horizontal line test that we discussed in a previous video, right? There's your 2 points with a y value of 4. And so when you find the inverse, if we graphed this, that would fail the vertical line test. It's not a function. So in order for a function to have an inverse function, it must be one-to-one. And because the functions are inverses of each other, the inverse function will be one-to-one as well. So we already did this. We graphed x squared. No, it was not 1-to-1. Failed the horizontal line test. Sometimes we can just look at part of a function and restrict the domain so that it is 1-to-1, and therefore we can talk about an inverse function. If you want to take a trigonometry class, you'll do this with some trig functions. But let's do this here for x squared. I'm going to draw it again here so we can see it. So this was not 1-to-1 because we have duplicate y values showing up, fails the horizontal line test. But if we could essentially just delete part of that function, then the rest would be 1-to-1. So basically, if you keep the vertex and you keep the right half of the parabola, but you don't use the left half, now it's 1-to-1, right? Now it passes the horizontal line test. We're not hitting 2 points with any of those horizontal lines. And if you made a table, you would only see each y value showing up once. You have 0, 0, 1, 1, 2, 4, 3, 9. You wouldn't have any of those duplicates from the left side. So what did we graph here? We graphed part of this function. We just restricted the domain. We only used x values that were greater than or equal to 0. Right? We started at 0 and we used the right half. And we could have used the left half, but we chose to use the right half. So we only graphed this function for x values that are non-negative. And so now if we wanted to talk about an inverse function for this, we could. Here is the table for what we just graphed. Just listing some of the points there. Now if we want to talk about an inverse, we'll have 0, 0, 1, 1, 4, 2, 9, 3. Now we're not going to have any duplicate x values because we don't have any duplicate y values in the first table. So now this function with a restricted domain is 1-to-1 and therefore has an inverse function. And you might recognize this. This is the square root of x. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, etc.